Hey everyone, and welcome back to this class, Advanced Convolutional Neural Networks. In this lecture, we're going to look at how to recreate content in code. Remember that this is the first half of style transfer. The basic outline is this. We're going to grab an image to use as our content. We're going to create a VGG network that stops at an intermediate convolution. We're going to build up the loss function and the gradient, and then use SciPy's optimizer to solve for the ideal input image. So at the very top, we have a function called VGG16 average pool. The purpose of this function, since it's not that obvious, is to recreate the entire VGG network, but with average pooling instead of max pooling. The reason why we do this is because it's been observed that average pooling yields better results than max pooling. This may be because average pooling keeps all of the data from the previous layer, whereas max pooling just throws data away. There is still a loss of information because you're merging all the pixels together, but you still get more information than you would be just throwing away pixels. So to do this, basically we create a new sequential model, and then we loop through every layer of the original VGG. At each iteration, we check the class type of the layer. If it's a max pool, we add an average pool instead. Otherwise, we just add the existing layer to our new model. The next function is VGG16 average pool cutoff. We don't strictly need this, but it follows the same pattern as the previous function, so there's just less new things going on. Basically, what this does is create a partial model. Recall that we want to compare the output at an intermediate convolution, so this function allows us to specify how many convolutions to include. VGG happens to have 13 convolutions, which is why there's a check in this function to make sure the number of convolutions you're asking for is between 1 and 13. Remember that you can check the architecture of a model at any time by calling the summary function. Next, we have the unpreprocessed function. We need this because, as you recall, when you try to use matplotlib to plot an image, it expects RGB, whereas VGG expects a different format. Basically, this just does the reverse of the keras function preprocess input. Next, we have the scale image function. The reason I wrote this was because I had some instances where matplotlib was complaining that it couldn't plot the image because the values weren't between 0 and 1. So this outputs pixel intensities between 0 and 1. Next, we have the main section. In terms of getting the data, it's going to be much simpler than before. We have no data sets to use here, which is actually awesome. So you don't have to worry about generators, data augmentation, and so on. I chose an elephant from the Caltech 101 dataset, since that's what I happened to be working with at the time, but you are of course welcome to use whatever content you wish. Next, we use the keras function loadImage to load an image. Note that this returns an actual image object and not a NumPy array, so the next thing we do is convert it to a NumPy array. Now because neural networks expect to take in batches of images, we have to add an extra dimension to the front of the image, so instead of just being height by width by color, it becomes 1 by height by width by color. Finally, we preprocess input, which needs to be called before the image is passed through VGG. Next, we create a content model by calling the VGG16 average pool cutoff function we made earlier. Just as a reminder, you're welcome and encouraged to test out the results at different layers. Next, we create the target, which is the model output given X. Next, we define our loss. This is just the mean squared error between the symbolic content model output and the target which we just made. If you need help remembering how symbolic variables work, you'll want to revisit modern deep learning in Python, where we discuss that in depth. Specifically, understanding Theano really helps with this. Next, we get the gradients. Note that these are all symbolic as well, the gradient loss and the model inputs. Next, we create a callable function that can take in a NumPy array and return a NumPy array using the symbolic variables we just built. This works just like Theano, so if you know Theano, then you're probably very comfortable with this notation. Next, we create a wrapper function just like we discussed in the slides. This is going to take in a 1D vector, reshape it into an image, then call the loss and grads function we made earlier. After we get the loss and grads, we flatten the grads back into a 1D vector, and then cast both to float64 before returning. Finally, we're ready to optimize our image. So I've included some timing code here to keep track of how long everything takes. To begin, we create an empty list to keep track of our losses, and we initialize a 1D vector x to be our initial guess into the minimizer. Next, we enter the main training loop, and we only need a few iterations here. So we call the fmin function, which returns a new vector for x, the loss itself, and another thing we don't care about. Notice how for func we pass in the wrapper, for the initial x we just pass in x, and for maxfun we pass in 20. This is going to let the fmin function do a few steps on its own, but remember that we want to alternate between minimizing and clipping. So next we clip x, print out the loss, save the loss, and continue the loop. When we're done the loop, we plot the losses, reshape the vector x back into an image, and reverse the pre-processing so that we can display it. Finally, we scale the image before plotting it. So let's run this and see what we get. So this is working as expected. We generate an image that has captured the main features of the original. As a follow-up exercise to this code example, what I want you to do is this. Try other content to see how it looks. Also try using the output at different convolutions from VGG. You should be able to see a clear transition from very sharp to very blurry as you go from the beginning to the end of the network.